So let's start. From the little quiz which I did, so I'm getting an understanding that not everyone has a good grip of ARM, which was sort of a prerequisite, but that not a problem. I'll try to go slow as much as possible, and I'll try to introduce to this topic as such that you can explore this topic moving forward after this lab. And I don't want to waste your time, so I'll please keep asking questions in the chat or try to interrupt me in any way so that I can help you out. And I hope you make the best out of this 2 hours. And thank you for attending this talk. So let's get started. So today we are going to cover the topic, the art of writing an ARM shellcode. So we will also look into what is it, how is it different from other architecture, what is ARM, how is ARM different from other architecture, and why you should be looking into ARM. So a little bit about my introduction. I work as an IoT security researcher at Payatu. Payatu does security research in a lot of stuff from range of products, and I work in the IoT division, and we do a lot of security related to IoT. So I have been speaking and training, delivering training on IoT in various conferences. I have interest in binary analysis, reverse engineering, and bug hunting and all that. So you can check my blog. I keep updating whatever on the topics which I'm interested. I keep posting stuff. And if you want to contact me, then you can contact me on Twitter. And if you look at any code which I've put on open source, then here's my GitHub link. Let's get started. So this lab is divided. This workshop is divided into 3 sections. First, I'll give you a high-level overview of what is ARM instruction set, what is ARM architecture, and all those all the instruction set that ARM has, and what is the ARM architecture. And in the second part, this will be covered in the first half an hour of the session. In the second 1 hour. In the second part, we will have shellcoding labs. So this is where all the action will be. And in that, we will write 3 different types of shellcode. First is a very introductory shellcode, spawning a shell on your local system. But the second and third are a little more practical and a little more tough. So you will have to be very focused in that part. And the last, so this lab will last for 1 hour. This section of the workshop will last for 1 hour. And in the last part, we will see what is a bare metal system and how can you write a shellcode for bare metal system. It is quite different from writing shellcode from, let's say, for Linux or Windows. So we'll look at the different. And I have one device which is ARM based, and we will try to exploit that, and I'll show you a demo of that. So starting with the architecture, ARM is a RISC instruction set architecture. So in the processor design world, there are 2 schools of thoughts, which is CISC, which is complex instruction set. On this philosophy, all the Intel-based microprocessors are designed. And another thought, CISC school of thoughts thinks that we should have a lot of instruction and very few registers to design a processor. On the other end of the spectrum is RISC, which is RISC, reduced instruction set computing. Basically in this, you have a very few instruction, but you have more register space to do the operation. So ARM is based on RISC architecture. It is not fully RISC compliant, but it follows major RISC principle. So it's a load store architecture. So basically there are only 2 instructions which will bring the data from the RAM in the processor and transport the data from processor to RAM. So there are only 2 instructions to bring the data back and forth between RAM RAM in the processor. So all instructions are fixed size 32-bit or 16-bit, which is not the case for let's say x86 architecture, x86, x64 architecture. But in ARM, all the instruction size are fixed 32-bit or 4-byte in size. So ARM has fairly large register bank. If we compare to Intel, it has only few registers, while ARM has more, 15 or 16 registers, which is our 32-bit size. Or if you go for ARM 64-bit, then it has 64-bit size. So it has 3 address formats. I will explain this more when we see look at some of the examples of the instruction. It has standard pipeline, fetch, decode, execute, which is part of any processor. So ARM is unique in its execution, which it has multiple type of execution. What you can say is mode of execution. It is first is ARM, which is 32 4-byte instruction fixed. It can also switch to thumb mode of execution, which has 2-byte instruction size. It has subset of instructions which ARM supports. Another is thumb extension, which is a mixture of ARM and thumb. So it gives a little bit more flexibility. Jazelle is basically you are running a Java application on ARM, which is this was designed because some people thought that Java would be a big thing someday, but it could not be. So the next is, as I said, the thumb is 16-bit. Inside thumb mode executes 2 bytes instruction, and ARM executes 4 byte. Just like any other processor, it has multiple privileges level. So ring 0. So you must have heard of concept of ring 0, which is where the kernel runs ring 1, ring 2, ring 3. So ARM has also has those privileges mode: user mode, monitor mode, debug mode, and kernel mode of execution. So which has, in kernel mode, you have most privileged instructions running. So as we said, it has 16 registers. So, but some registers have some special purpose. For example, register 15 is called program counter. It actually holds the next instruction which ARM processor is going to execute, which is this register is called EIP in x86 architecture. In x86, it immediately points to the next instruction it is going to execute. But in case of ARM, the PC register points to the next 2 instruction ahead of the actual execution. So another register is R14, which is link register. So basically, when you have a code, you have if statement, else statement, call statement, and in those cases, your program jumps to some different address, and it gets back to the address it was previously executing. So this is what link register helps you to do. It stores the next address from the address which it has jumped, so that it can return back. So this helps you to implement structures like if, else, call, and all those. So stack pointer points to the top of the stack. So stack is sort of a temporary memory space which the function is given during execution, so it can store the temporary data. A frame pointer points to the bottom of the stack. The range of memory is given to a process. Stack points to the top of the memory, and frame pointer points to the bottom part of the stack memory. So it has many instructions. If we categorize different instructions, then the first category of instruction will be data processing instruction, which will be basically adding, multiplication, division of data, and manipulation of the data. So this is basically doing mathematical sort of operation, which include arithmetic operation, logical operation, moving the data between the registers. So basically processing the data. So if we see arithmetic operation, then it supports all this instruction. add, subtract, and all those things. If we see bitwise operation, then it has AND, OR, XOR, left shift, right shift, and you have movement instruction. So the first, the next category of instruction is load store. So basically, this is the category. This is the instruction which I told you previously, that it will load the data from RAM into processor. So first is load data, which will load 4 bytes of data from address pointed by the register into a register. So here is an example, LDR, which is basically load register. R1 is pointing to the address from which it wants to load the data, and R0 is the register in which the data will be put into. Similarly, we have store another different version called LDRB, which will only load 1 byte in a register. LDRH will load the half word, and so on. So similarly, we have store instruction, which will have a similar structure to this. It will here have str, and it will put the data from R0 into the memory address pointed by R1. So this instruction are basically a single load store. Basically, you are moving the single unit of data, 4 byte, 2 byte, or 1 byte. But let's say if you want to move, copy an array of data from one location to another, so then you use this instruction, load store multiple. It's load multiple. So if we take the example of this instruction LDMIA, so which is basically telling load multiple increment after. So what it tries to do is, you can imagine memory as sort of a linear array, and from here you want to store the data in particular, copy the data in particular direction, let's say in the downward direction. So you want to copy data from 4000 to 7000. So what you will do is point the base register and say what kind of increment operation you want to do. Do you want to do decrease the address once copying the bytes, or do you want to decrease? So if you increase the address, it will go in downward direction. If you decrease, then it will go in upward direction. So this LDMIA, what it is doing is load multiple, increment after. So what increment after means is first increase the address. So if it is pointing to 60, the first increase to 64, and then copy the data into the register. So if we look at the example register, so LDMIA R0, R4 hyphen R6. So what it will do is it will load the data pointed by R0 into register R4, 5, and 6. So it will do 3 such operations, copying from the address into register. So this is what is IA means, increment after. It could be increment before. So first it wants to increment the address and then copy the data. The previous instruction first copied the data and then incremented the address. Similarly, you have store. So basically you want to store the data from R4 register to R6 into the address pointed by R0. So if you look at it this way, that it helps you to implement basic data structure, which is stack and queue. So basically if you do push and pop operation, so this decrement operation, if you do decrement, you're doing a push operation on the stack. If you're doing an increase, then you are doing a pop operation. So this is what it is used for. So let's look at an example. So if you try to correlate this C program into this assembly disassembly of this program. So it is passing two parameters. It is adding the data and printing the result. So here we can see that it is first doing a load operation. We said that the first, whenever there is an addition of any sort of operation that is happening in the processor, the data has to be in some register. So this is what this instruction is making sure of. It is loading the data from this address. into R2 register. Again, it is loading the data in R3 register, and then it is doing the add operation. Similarly, you have subtract operation and multiplication operation. So there are different addressing modes in ARM. Basically, you specify the base address of the memory, and then there is an offset, which is basically adding the offset to the base so that you can jump to different location. The first, there is a pre-indexing. Basically, you are, and this different mode of operation, what they are doing is what kind of result do you want to store as a result of this calculation. So first, you in the offset addressing, you apply offset to the base value, and the result is used as the memory address, and the register, which is RB, no changes are made to the register, which we saw previously over here. So this is offset addressing. Here we are subtracting minus 10, which is 16 decimal, but the result is not stored in FP. The address pointed by FP is not changed. Then there is a pre-indexing, in which basically offset is applied to the base register, and the result is used in the memory and returned back to the base register. So basically, the result of this calculation will be written back to this. Then the next is post-indexing addressing. Basically, the base register value is used as memory address, and offset is applied to the base address and returned back. So you saw that these are three different indexing addressing modes. So the next category of instruction are basically branching instruction, which is these type of instruction help you to implement if-else statement. So first is comparison. So when you see any branching instruction, the first thing it will do is generate a conditional. First, it will do is do some calculation on the data and generate a conditional flag, which is reflected in CPSR register. And next, then there will be instruction which will take the decision should they jump or not. So the CMP instruction will actually generate the instruction and test. So these are the instructions which will generate the condition. Basically, subtract two registers and see if register 1 is greater than other or something like that. The second instruction will actually do the jump. So there are different versions of the jump, which is B. So there are three different versions: branch and link, and branch, link, and exchange. So I'll explain you each one of them. The first one is branch, which is unconditional jump. Whenever a condition, this instruction is encountered, the jump is taken to the destination, which is pointed by a register. The next is branch and link. So in the first instruction, the return address is not stored anywhere. In branch and link instruction, we are storing the address from where we are jumping in a link register, and then we are making the jump. And the next is branch, link, and exchange, which is basically we are making the jump and also switching the mode of execution. So if the destination address is odd number, it will switch the execution mode to thumb execution. I know this is little confusing, but I'll repeat again. There are three different versions: branch, branch link, exchange. In the branch instruction, you are jumping to a destination address without storing the return address. In branch link, you are jumping to a destination address, but you are also storing the next instruction from where you are jumping in a link register. In branch, link, and exchange, you are storing the return address, and then you are switching to the different mode of execution. It could be from ARM to thumb, or it could be thumb to ARM. So this is basically, here we are not testing any condition. But if you want to do testing like equal to, less than, greater than, then you have a different version like branch, exchange, branch equal to, branch less than equal to, something like that. So these are those different conditions. So if you are doing a conditional jump, we will do if jump to the address only if the condition was equal to. So how do you determine if the CPU state is equal? The zero flag of the CPSR register will be 1. CPSR register is a state register which reflects the state of the calculation of your instruction. So these are the different conditions, equal to, not equal to, greater than, less than, equal to. So all these different instructions. So again, let's look at an example. This is a C program, and this is a disassembly of that program. So the first is we have 2 parameters. We are comparing the condition. If A is greater than B, then print A is greater than B. If A is equal to B, then print the statement. So if you look at the disassembly, first it is loading the data in R2 and R3 register. Then it is comparing the 2 registers, R2 and R3. And then we are taking the jump. Here there are 2 things you should note, is the address at which the jump will be taken if the condition is satisfied. And if the condition is not satisfied, then the branch body is executed. So if the condition is satisfied, then it will jump to 410 address. So here less than equal to. So here A was greater than B. But here the condition is BLE, which is basically branch if less than equal to. So if you notice, then this is exact, less than equal to is exact opposite of greater than. So if we want to skip the body of the code, if it is greater than equal to, less than equal to, I'm sorry. So you will execute the body if this condition is satisfied. Similarly, you have other blocks of code. So does anyone have any questions so far? I know this is a lot of things, a lot of content in so less time. But does anyone have any question? Okay, so let's move on to the next part. Should I move on to the next part, or should I explain the ARM instruction in more detail? Okay, let's move on to the next part. So we know how to write assembly at this stage. So what do we do next? What do we do next as an attacker having this knowledge? So basically, we will try to write shellcode, and so you must be having a question like, what is shellcode and why do we use it? So shellcode is basically a sequence of byte, which is a data to you, but to a processor, it is a set of instruction. Processor will interpret those instructions and execute certain command. So we saw previously what those command instructions are. And those instructions have some binary representation. So what we do as an attacker is somehow try to get this data inside a process memory, any process that we are trying to exploit. And if we can somehow redirect the course of execution to those bytes, then we can control that process, and as a consequence, we can control that machine. So this is what exploits try to do. What they try to do is find a vulnerability in an application. That vulnerability will basically redirect their instruction pointer, which is the PC register for ARM, EIP register for x86, and they will somehow try to redirect the execution to the data which they have injected into the program. So those sequence of bytes are called shellcode. So what makes a shellcode different from other assembly programs is they are position independent. So basically, wherever they are injected into memory, they will still execute without any problem. From where does this name comes from? So basically, when this thing was first practiced, it was only used to spawn shell, which is basically the command shell, which we use in Linux. But nowadays, it is used to do more sophisticated things like launching other process, terminating other process, opening a network socket, and copying the file, and all sort of things. And shellcode basically repurposes your program to run in some other manner in which it was not designed to do. So this is what the magic of shellcode is. So basically, if we talked about what is shellcode, but how does it does all this magic? What are those magical instructions which is making the computer dance left and right? So those instructions are called system calls. So what basically system call in a simple words are, if you look at any operating system, it has set of functions like opening a file, running a file, executing a file, opening a network socket. For example, if you have a browser, your browser will open a socket to the website you want to visit, fetch the data, save that file in your file system, and show it on your web browser. This involves doing a lot of operation on file and network. So shellcode is system calls are basically organizing that operations through a systematic interface. And whenever you want to do those sort of operation, you request these things, these operations to your operating system kernel, and your kernel runs those operations and reports back to you. And it won't run this blindly. Of course, it will coordinate it with the hardware, and it will coordinate it with other processes and see if does the user who is requesting this resource, does he have the permission? Should we move ahead with the operation immediately, or should we defer it for some later time? So all those things are done by the kernel, and those things are done requested from user mode application, which is less privilege, to the kernel mode, which is higher privilege. So how do you make this call? Basically, the next question arises: how do I interact with the kernel? How do I do that? So this is where calling conventions comes into picture. So we will take all the example in this workshop with regard to Linux. So Linux has a standard defined interface. Whenever you want to make a system call to a kernel, system call is basically making a function call. So you have to load the function call number, system call number in R7 register, and those function will of course have some parameters which will be what sort of operation you're doing. So you load those parameters from R0 to R6. So basically you have 6 parameters, and if you have parameters which are more than 6, then you load those parameters on the stack of the process, and the kernel will read out that data from the process memory. Once you have done the setup, you raise an interrupt from your user mode. User mode is less privilege mode, so it cannot change data of higher privilege mode process. So when you raise the interrupt, kernel comes into the picture, it reads all the data, performs all the operations it needs to do, and returns the value in R0. So any function call will of course have a return value. It may or may not have, but in case if it has, then the data is put into R0 register, then the user can read that data from R0. So if we carefully look at some of the system calls, and if we understand, yeah, sorry about that. So does anyone have any question about this system call, or how to make a system call? So this is going to be really important moving forward. I think so we are good. So before we move forward, I'll introduce some of the tools which I use on daily basis, and these are really helpful and nice open source tools. So this will also help you to do your job. So GDB is basically a debugger, which is basically when a process is running, you want to halt it, inspect it. So the GDB will help you. GDB is command line based, and it is not so user friendly. It is very helpful, but not so user friendly. So PointDBG is a GDB plugin, which makes it very useful and easy to use. When you are writing an exploit for any program, there are certain set of operations which you do on daily basis. So there is a Pond2 exploit development library which is based on Python. A lot of city players use it. It is very common. So I would highly recommend to look into this. So whenever you are writing a shellcode, there are certain steps which is basically converting a C program into assembly. Assembly program into machine language and linking step. So this is done by assembler and linker. So if you are writing a process for any particular target architecture, then you should be looking assembler and linker for those target architecture. The next is system call tracing. Basically, as I said earlier, that when you are making, when your program is running, it is making a lot of system call to your kernel. And if you want to know what all system call it is making, then you can use strace, which is a Linux-based tool. So it will give you all the system calls and what all parameters data was passed to it. So this is a really nice reverse engineering tool, very helpful for the case of Linux. OBJ-dump is basically when you want to disassemble any program. So basically you don't have a source code to the program, you just have the binary. Then disassembling the program will help you. And if you know the instruction set for that particular architecture, then this should help you. OBJ copy is basically copying and editing of binary files. So I will be repurposing OBJ copy to extract shellcode. We will see moving forward how is it going to help us, but this is basically help you to extract shellcode when you have completed writing your shell. So this is a general shellcode writing step or algorithm or procedure which I follow. Usually I don't write the shellcode right away. What I do is I go in Google and search for shellcode. Of course, a lazy approach always I prefer to do that. But often the case when I'm writing a shellcode which is very specific to my use case, and if I'm not able to find it, then I follow this step. But if you can find open source shellcode which is out in Shellstorm, which is a popular shellcode sharing site, or HITB, then you should use that, make some edit to that. Why put the extra effort if you already have a ready-made shellcode? But if you don't find, then this is the general procedure which I follow. So first is basically write whatever program that you are trying to emulate, try to write that in higher level language. Which tool of my choice is C language. So it will help you to write fine-grained, low-level system calls. Then using strace, which the tool which you mentioned previously, you try to trace what all system call those functions are making. Try to understand the parameter. Try to understand what all system call number you have to write. Note down those parameters, look at the system call manual and see what are the parameters in what manner you have to pass. And then re-implement this C program in assembly. Try to understand, then this is your first stage. This is your first stage. You have basically converted your C program into assembly language and you have extracted the byte, but your input program on what you are targeting will not always welcome those bytes. It will have some filters, like it will not accept any null filter in the input which you are giving, or it will have some other sort of filter like alphanumeric only data it is going to read from the file into its process memory. So you will have to bypass this filter by writing instruction which satisfies this instruction, this constraints. So this step might differ from target to target, and this might also increase the payload size of your shellcode. The next step is reorganizing the whole payload such that you can compress the size and do other signature detection or signature bypass operation. And then the final stage is compile the code and extract those bytes. So let's start with our first lab, spawn a shell. Basically, shell, the reason for doing is this is sort of a hello world for shell coding, and the system call corresponding to this is execve, which is basically you're telling Linux kernel to load the binary and run it. And we have the parameter R0, R1, R2, and R7. So R0, we have 3 parameters. And in the first parameter, you have to load /bin/sh. So this is basically the program which has your shell. This binary is present in almost all Linux. So people use this binary path. The second and third parameter will be learned. We don't want to pass any argument to the shell. You could pass argument if you want to execute any particular command, but here we don't want to do that. We just want to open a shell. And then the third is the environment variable, which is basically you want to set up environment. You want to set an environment variable. And the third is R7. So I will demonstrate this lab to you. I will execute all those commands, and then I'll give you some time to run it yourself. So if you go to labs directory, I have shared the lab files in Discord channel. So if anyone has any problem getting those files, then let me know. Can everyone see the screen properly?
Yes.
Yeah, it looks pretty clear from here.
Okay. So any program has 2 sections at the very least. First is the code section. First is the code section, which will have all the code basically which the program wants to execute. And the second is the data. Any program is a mixture of these 2 things, no matter how sophisticated the program is, even in your web browser. So if we look at this assembly, the first thing we are doing, we are declaring a section which is a text, which is as a code. We are declaring global start. This start means that this is from where I want to start executing my code. This is all the code that we want to execute to run a shell. So what this is doing is adding 1 to the PC. So can anyone tell me what is this trick doing? I'll give you a hint that we talked about this in ARM mode of execution, ARM mode or thumb mode of execution. You can type it in the chat if you don't want to talk. So what this basically is doing is, it is the .arm mode. What it is doing is, it is telling that the next instruction that you see are in ARM mode. So this instruction will be 4 byte in size. These 2 instructions will be 4 byte in size. And by doing PC, so we said that 3 ARM instructions are in 3 addressing format. So basically, we have 3 parameters to this instruction add. We are adding 1 to the PC and storing the result in R3 instruction. So now R3 is loaded with the address where we want to jump, which is basically PC plus 1. We said that PC is 2 instructions ahead. So when your PC was here, it was actually pointing to this address. And we did add 1. So we are basically making the PC an odd value by adding 1. It was even when it was pointing here. We're doing a BX R3, what we are doing is branch exchange, which is basically we are branching to this address, which is here, and we are doing exchange. Exchange is basically switching the mode of execution from ARM to thumb. So here, and then in this code we declare that this is a thumb instruction, which is basically 2 byte in size. Each instruction is going to 2 byte in size, and we are switching to thumb mode. We are declaring this section as thumb, and over here we are switching to thumb mode. Here it is executing this system call. So we said it has 3 parameters. So first is the path of the binary it wants to execute. So we are loading the address in R0. So this is pointing to this string, and it is loading the address in R0. Then we are doing XOR R1 with itself. Whenever you see this type of instruction, what it is trying to do is put the value of 0 in R1. The reason we are avoiding doing move instruction R0 into R1 is we want to avoid a null byte. The reason for avoiding null byte is whenever you're injecting the data, so usually the vulnerability is in strcpy function, which is basically copying the data from source buffer to destination, copying string data from source to destination, and the string is a null terminated data. So until and unless it will encounter a null value, it will keep copying the data. So we want to put a null value at the end of this string. It does not have a null value here. So that is why we are putting R0. That is why we are putting 0 into R1 and R2 register. There is another reason for doing that also, but over here we are nulling the value of R1 and R2 register. Here we are doing strb, which is basically store a byte from R2 into this address ending spawn line, which is pointing to the end of this string. Once we have stored this, we want to set null value to parameter second and third. This is what these 2 instructions are doing. And we are all good to go at this point. After executing these 3 instructions, we have set it up these 3 parameters. And then we are loading the value 11 in R7. 11 is basically the system call number for execv, which is executing the system call. And then we are raising the interrupt, and which will basically execute, make a kernel call, and kernel will execute the call. So I will demonstrate you this working. So is this size of the shell good enough? Or?
Yes, it is.
Okay. So if we look at the make file, if we do make shellcode, it will execute these through a command. So if you, I have passed the PDF to set up environment in the Discord channel, and it will give you instruction on how to install these AS and LD. These are basically assembler and linker, which we talked previously. With doing AS command, we are basically assembling the code, which is converting the shell assembly language into binary. Loader will basically reorganize that binary into a file format which the operating system understands, loading the data and copying the data in different sections in different file format. And we have a shellcode file. So let's see what the shellcode file is. It is ELF file, 32-bit, and it is in ARM format. So another very helpful tool is QEMU. QEMU is basically help you to execute foreign architecture in your machine, which will basically allow you to execute ARM code on Intel x86 system. And this is really helpful in case you don't have the hardware. And this is the also reason I put it in this workshop, is because we got shipping the hardware would be difficult for everyone. So we will use QEMU to execute this system call. If we do QEMU arm command and -strace. So strace is a tool which we said in Linux tools trace the system call. But if we pass -strace, then this this QEMU will also emulate the function of that system call in this. So if you do shellcode, oh, it is crashing. Interesting. Okay, I think I am executing the wrong one. So if you see over here, we are able to execute this shellcode. When we did strace, the QEMU printed out what all system call that were made with this. So I guess this is the end of this lab. If we do a quit, this will. So I'll give you 5 minutes to execute this. So you guys can start. I'll put a timer. If you have any question, then please ping me. Okay, then let's continue. So there are a couple of interesting things that we can note in this shellcode. The first thing is how we made this thing machine position independent. The first thing I said that the shellcode is position independent so that it can be injected anywhere in the process and it can run. So we did that by. So first we needed the address of this string /bin/sh. So we did that by putting an offset into this, which was at the end of this shellcode. So whatever the shellcode is generated is within this area only. The reference to this the data is at the end of the shellcode. So it is addressing at the end, and it is doing a PC offset, basically from where the current offset is PC is pointing to this instruction, and from that it is offsetting to this string. Then we use the technique of switching the mode from ARM mode to thumb mode. In the ARM mode, if we look at the disassembly, if we look at the disassembly of the code, then the first two instructions were 4 byte in size and the rest of the instructions were 2 byte in size. So this has reduced the size of our overall shellcode. I said that we are doing a PC offset, so to load the address. So this is, you can see the address over here. It is doing PC +8. So from here, when you are executing this instruction, it is pointing to this instruction, and +8 is going to point to this particular address. You can see over here, it is mentioning over here 1068, which is this address. The next is null byte elimination. So this is, of course, it depends on target to target. And in this case, in often the case, you are targeting the strcpy function, so it will avoid, you don't want to put any null bytes in that shellcode. So here you have null in this instruction, svc 0. But you can change that by putting this value. We saw earlier that we did svc 1. In earlier Linux specification, you specify the system call number in the parameter svc, which is now changed to R7. So if you put anything over here, it won't matter. And if you want to put any particular number in register, but that number has 0 in it, so what you can do is doing some putting a number which is non-zero and doing some manipulation on that register, and you will get a result such that it has a non-zero number. So this is one example. If you put this 1 in R0, then you will get this instruction which has a lot of null bytes. So you have a set of instruction which will give you the same result as this, but some extra calculation effort is put into this instruction. Next lab which we'll do is spawn a TCP shell. So does anyone has any idea what is this about? Spawning a TCP shell. So basically in TCP shell, you are starting a TCP socket server on the process which you are exploiting, and then binding the descriptor of the TCP file with the shell process. So any process which you open, even if it is doing absolutely nothing, it will open 3 descriptor in its process, which will be std in, std out, and std error. This will be available for all the process in your system. And the idea of file descriptor is basically when you open a resource, particular resource, then the operating system will return a file descriptor. And based on that, which is basically an ID for a process, and to manipulate that resource further, every time you make a system call, you pass the file descriptor ID. So when you open a TCP shell, TCP socket, you have to do series of system call. The first system call will be notifying operating system, hey, I want to open a TCP shell. The operating system will return your file descriptor, and then you do other operation like listen on that particular file descriptor. What interface are you going to bind? What port are you going to bind? Once you have a TCP socket running, then you link the file descriptor of your TCP with the file descriptor of std in, std out, which will basically give you a shell. So in this shellcode, you start a TCP server, you run a shell, and from another terminal, you do a TCP connection to that particular address, and you can then communicate between those with that socket. Again, with this lab, I'll give you a demonstration. I will explain you the shellcode, and then I'll give you some time to run it on your own. So for this, you will have to go TCP bind shell. So as I explained to you earlier, my first approach is write this shellcode in a higher level language, which is of my choice is C. So if we understand this as a higher level language, we have a socket. We are opening a socket. It gives a file descriptor. Then we want to bind to a particular address, that what address you want to open this file descriptor on. So this is my IP address, my local IP address, and this is the port on which the socket will be opened. I bind the file descriptor with this address. This is a data structure. This is a structure, and we make a bind system call. First we make a sock system call. Then we make a bind system call, basically binding, and then we are listening for client, do a listen system call, and then we are accepting client on that socket. Once we have a particular client, we have a new socket, and then we do a duplicate system call on those socket and run it on then we run execs CVE. So this part of the shellcode can be borrowed from the previous shellcode. And then once we have executed all this command, the client may issue the exit call and we close the socket. So let's compile this program and trace all the system call it is making. So if we do make program, it will compile the program. Then let's do strace, and if we do when we do an strace, it's not executing properly. So let's try to understand this. When we did strace, the operating system itself is trying to run this program, and then there are a lot of system calls which are related to loading the file inside the process. And then let's try to do a sock. Let's try to search for socket system call. Okay, so here we have successful open. So here we are loading this program. Then a bunch of system calls are made. And then we can see over here, the sock system call is made. These are the same parameter which we passed in our program. And the return value is 3, which is the file descriptor which I mentioned to you. With that file descriptor, we are making this call. File descriptor is the first parameter. If we look at this, file descriptor was the first parameter which was written from here. Then we are passing the data structure. The data structure is represented over here. 4 port and the IP address, and this is 16, which is basically the size of the structure. Then we do a listen call. Listen on that same file descriptor and number of clients we are accepting, and we do accept on that same file descriptor. Now let's try to connect to this particular address and on port 444. We use netcat, which is basically a program that creates a socket, TCP socket. So if we look over here after socket, there were a lot of system calls over here. After accept, we did duplication of the file descriptor. Then we executed exe, exec, bin sh, which we can see over here in the program. And there are other bunch of system calls which is basically loading this particular program. So these system calls are related to that. And now we are reading from R0, which is basically std. So let's execute one command from this ls. So we can see strace is simultaneously tracing this from where it loaded the program, and see, we can see this is the same folder from which we did the command. Okay, so now let's try to understand how will we do this same program in assembly language. If we go to TCP shell over here. So as I said, I usually look for open source shellcode. I borrowed this shellcode from this link, exploit DB, and you can look at the shellcode. Over here, first we are using the same trick of switching from ARM to thumb mode. Once we are in thumb mode, the first thing is we do a socket system call. We set up the parameter, R0 will be 2, R1 will be 1, and so on. We set up the parameter. Once we have this, we do the second system call bind. And bind, after doing bind system call, we are doing listen. And listen is again using the parameter, a file descriptor parameter, which we have saved from the first system call. We are moving the R0 into R3, which is basically saving the, making a copy of file descriptor register. After doing a listen system call, we are doing accept. Accept will basically accept the client. And after doing accept, we are doing dupe system call, which will basically execute this particular piece of code. And then exec CVE basically start a shell in that process. Struct address is basically where we want to avoid null bytes and also want to load the address. So this is a structure which is stuck at the end of the shellcode, which is basically the data. And again, this is another data, which is the address of bin sh. So let's try to execute this. If we do make shellcode, then it will run this particular shell. It will run assembler and linker, and it will generate the binary. If we do obj dump Linux obj dump, then we get this shellcode, disassemble, compiled. When we want to extract the shellcode, all we have to do is extract these bytes in this particular column and pass it into a program to run. Let's try to run it in QEMU ARM. Let's also try to do strace along with it and shellcode. So here we see a more filtered output from the previous program. It is only executing the shellcode which are necessary. In the previous program, there were a lot of unnecessary shellcode that were getting executed. Let's execute this NC, and we can see that this is writing the same data over here into this, and let's execute the command. So we can see the reason we don't see the system call over here because the exact CV is started in another process. But you can see that this shellcode is and executed successfully. I'll give you 10 minutes of time to run this exercise yourself. If you have any problem, then let me know. If you have any question, then also please fire.